So I'm not going to go too deep into the visualizations, but I leave that up to you to do on your own. And there's a lot of great resources showing what the linear combinations look like in terms of the resultant and the different parallelograms that you can make. I'm going to just keep it very simple and use these vectors V with this transition matrix to show that there is a linear combination of these coordinate vectors that can express V in terms of the t basis. And you see, we're already kind of doing that, and we have three equations and three unknowns doing this. Now, we know that this leads to something like this, and we see that these are in two different sets. And what we want to do is make a linear combination of the entries of this transition matrix of the vectors that we have in the basis S. How we do that, and I forgot the brackets. Sorry about that. And so how we do that is going to be just like this. If we think W1, we're going to just use this right here. 1, because that's what our basis is. 1, 2, negative 1. 1, 2, negative 1. As a linear combination, we can clean this up a little bit, and we can just make this. So now we've just formed a linear combination, and the reason why we took these numbers right here we go, we just take these numbers and form a linear combination. And we do that by almost kind of like, think about taking the transpose of this, so that we, instead of having now a column, we basically have just kind of flipped it now, and we have made it a linear combination. And V1 spans the row now. And so that's the intuition behind kind of doing something like this and making this a linear combination. Substituting this for now augmented matrices and other sorts of matrices, this is going to be a vector. We are expressing V in terms of T. So we've taken these vectors, we've multiplied them, and now we are going to get back W1, which is in terms of T. Okay. Now we do the same thing for the second one that needs to be represented as, and we'll put this in purple. And you can see that I got this from, the second column now. And you can guess that the third one, I'll use all the way down here to calculate W3, the third. And what these are called are basically the coordinates with respect to another basis. And so now we have W2. We can solve this. Great. Now you can see that this is W2. So now we just need to find 3. And vector 3. And you can see we're just kind of distributing the scalar into here. And now we can write V, the coordinate. We've changed our perspective now. We've changed our perspective from this first basis. And as you can see, we've changed basis now from S, which is composed as these original bases, to T. And because this is the transition from T to S, we already know that we are in S and we want to go to T. So we use this transition matrix and we made linear combinations of all of these vectors. And we determined that all of these elements in this set of the basis T are now being expressed in terms of T for V. I know that's like really confusing, but all it means is we've taken these vectors and we did some operation that changed our perspective about what these are. And instead of being V1, they are now W1 and W2 and W3. Because we did this transition matrix to change our perspective about where the bases are. So these are now mapped to different bases. We've just done a sort of transformation. So all these v's just went to these w's, and now they are in terms of basis t.